In this lecture, I am going to solve some numericals on crystal structure. The first numerical is an unidentified metal crystallizes in a BCC structure with a lattice constant of 3.039 angstrom and exhibit a density of 5.81 gram per centimeter cube. Determine the atomic weight of this metal. So in this numerical, let's see what are the given quantities. Given quantities. The given quantities, the structure is given. Structure is BCC. When the structure is BCC, it means effective atoms per unit cell is 2. Effective atoms per unit cell is equals to 2. So that is given. Then the third quantity is lattice constant is given. Lattice constant, which is A, and that is equals to 3.039 angstrom. So this is given in angstrom. Let us convert that into meters. So that is equals to 3.039 into 10 to the power minus 10 meter. Then the fourth quantity given is density. As you can see here, the density is given. Density rho, which is 5.81 gram per centimeter cube. This is in CGS system. Let's convert that to the MK system. So that one is equals to 5.81 into 10 to the power 3 kg per meter cube. This is in MK system. Then as you know, we may require the Avogadro's number for this. So Avogadro's number, you must know that. Avogadro's number denoted by n suffix a, and that is equals to 6.023 into 10 to the power 23 per gram mole. This is given per gram mole in terms of per gram mole. So that is nothing but equals to 6.023 into 10 to the power 26 per kg mole. So in MK system, we will consider kg mole. And what we have to find is atomic weight. Atomic weight we have to find. Now the formula which we're going to use for this sum is AQ is equals to N into M divided by rho into Na. Na is Avogadro's number. In this formula, A is the lattice constant, N is the number of atoms per unit cell, M is atomic or molecular weight, rho is the density. What we have to find is, we have to find atomic weight, that is M. So M is equals to AQ into rho into Avogadro's number divided by effective number of atoms per unit cell, that is N. All these quantities are given. A is given, which is 3.039 into 10 to the power minus 10 in terms of meter, and we have to take cube of this into density. Density is this 5.89 into 10 to the power 3 kg per meter cube into Avogadro's number, which is 6.023 into 10 to the power 26 per kg mole. So all these three quantities are given here, and that divided by effective number of atoms. So for BCC, effective number of atoms are 2. So when you simplify this, you get M is equals to 49.12 AMU in atomic mass unit. So remember that in this formula, M is in AMU, and it converts to the kg when M divides by Na. But in this formula, M is in AMU, that's why we are dividing it by Avogadro's number. So that's sum number 1. Then let's go to the sum number 2. Sum number 2 is copper crystallizes in FCC structure. Its density is 8.96 gram per centimeter cube and an atomic weight is 63.5 AMU. Calculate the distance between the two nearest copper atoms, and the Avogadro's number is given. Not necessary that every time Avogadro's number would be given, you must know Avogadro's number. So let us see what are the given quantities. In this case, given quantities are, the structure is given. First, structure is given, which is FCC. And when the structure is FCC, it means that atoms, that is small n, is equals to 4. Effective atoms per unit cell are 4. That is given. Then the third quantity is density of the copper is given. As you can see here, density of copper is 8. Let us denote the density by rho. That rho is equals to 8.69 gram per centimeter cube. Let's convert this in MKs unit. In MKs, it is 8.69 into 10 to the power 3 kg per meter cube. So that is the density. Avogadro's number is given here. Avogadro's number is given Na, which is 6.023 into 10 to the power 23 per gram mole, which is equals to 6.023 into 10 to the power 26 per kg mole in MK system. And what is asked is you have to calculate the distance between two nearest copper atoms. So to calculate that d, that is the distance between two nearest copper atoms, first we have to find lattice constant A. So we have to find lattice constant and then interatomic distance. So let us first find lattice constant A. We know the formula for lattice constant is A cube is equals to n into m divided by rho into Avogadro's number. RHS sites are given here. So this is equals to n. Small n is given, which is 4, into atomic weight is given 63.5. I have not written here. One more quantity is given, that is atomic weight, which is 63.5 AMU. So this is the formula. So 4 into atomic weight, that is 63.5. M is 63.5 MU divided by rho. Rho is 8.69 into 10 to the power 3 into Avogadro's number is 6.023 into 10 to the power 26, and that is equals to AQ. So if you simplify this, then what you get, 252 upon this 5.234 into 10 to the power 30, and that is equals to 48.15 into 10 to power minus 30. This is equals to AQ. And so the A is equals to 3.638 into 10 to power minus 10, and this is in meter. So we got the value of A, lattice constant, which is 3.638 into 10 to power minus 10 meter. Now we have to find this interatomic distance. This is the first. We got the lattice constant. Second, we have to find interatomic distance. To find the interatomic distance, as we know that this copper is having FCC structure. So the atoms are in contact with each other along along phase diagonal. Okay, atoms in contact along phase diagonal, because this is FCC structure, and the phase diagonal is equals to root 2a. We have studied this. Phase diagonal is equals to root 2a, and that is equals to 4r. Okay, that is equals to 4r. So this 2r is equals to then a upon root 2. 2r is equals to d, which is interatomic distance. Okay, this 2r is equals to d, that these two atoms are in contact with each other. So this 2r equals to d, and that is nothing but interatomic distance. And this interatomic distance is equals to a upon root 2. We know the value of a, just we calculated. A is this. So the A is equals to 3.638 angstrom. This is in meter, so that is equals to 3.638 angstrom. So what we have to find is D, and that D is equals to A by root 2. This is A in terms of angstrom divided by root 2. This is interatomic distance, and this is equals to 2.5. angstrom. So interatomic distance, the distance between the two copper atoms is 2.57 angstrom. So this was the second sum. Then let's go to the third sum. Cesium chloride has simple cubic diatomic structure. So this cesium chloride is simple cubic diatomic. This is given. This is a simple cubic diatomic structure is given. Then cesium, in which cesium plus ion is at body center of the unit cell. Chlorine ions are at 8 corners of the unit cell. And what we have to calculate is density, packing factor, and lattice constant. And the given things are, see, the radius of cesium ion is given, which is equals to 1.65 angstrom. This is the radius. And so the diameter of cesium ion is equals to 1.65 into 2, and that is equals to 3.3. 3.3 angstrom. Also, radius of chlorine ion is given, which is 1.87 angstrom. And so the diameter of chlorine ion is equals to 3.74 angstrom. So this is given. Similarly, its atomic weight is given, which is denoted by N. So atomic weight of cesium ion is equals to 132.9 AMU, and atomic weight of chlorine ion is 35.45 AMU. So these things are given to us, plus cesium chloride is simple cubic diatomic structure. And in case of simple cubic diatomic structure, atoms are in contact with each other along the body diagonal. We can say atoms or ions. Ions are in contact along body diagonal. And we know that body diagonal is equals to root 3a. This is the body diagonal of the cube. And along this body diagonal, atoms are in contact with each other. So this is equals to diameter of cesium ion plus diameter of chlorine ion. If you have a confusion, I can show you the diagram for this. So this is the cube, and in cesium chloride, as mentioned here, the chlorine ions are at 8 corners. These are the chlorine ions which are at 8 corners, and at body center there is cesium ion. And these ions are in contact with each other along the body diagonal. So this is one body diagonal. So along this body diagonal, these ions are in contact with each other. So this is, twice the radius of cesium plus ion plus twice the radius of chlorine ions, which is equals to root 3a. Or you can say the diameter of cesium ion plus diameter of chlorine ion, that is equals to root 3a. So you must know this. So from this what you have to find is the lattice constant, and so the lattice constant A is equals to diameter of cesium ion plus diameter of chlorine ions divided by root 3. So we know the diameter of cesium is 3.3 angstrom. So 3.3 plus diameter of chlorine, this is the diameter of chlorine, 3.74 divided by root 3. So that is equals to 7.02 by root 3, which comes around 4.053, and this is in angstrom. Your diameters are in angstrom, so this is in angstrom. So we got the lattice constant A. If you know the formula for lattice constant in case of simple cubic diatomic, you can directly write this formula and solve the problem. If you don't remember, then you can draw the diagram and find out what is the formula for that. So first, what we have to find was lattice constant. So we got the lattice constant. Second, we have to find the packing fraction. We also derived the formula for the packing fraction. So packing fraction, you know that it is defined as volume of effective atoms in the unit cell divided by volume of unit cell. Now this is a simple cubic diatomic. In SC diatomic, effective number of atoms, that is the value of N, is 1 cesium ion plus 1 chlorine ions. So in this case, it is a volume of cesium plus volume of chlorine divided by volume of the unit cell, which is AQ. You can write directly this formula of A, or you can directly write the value of A. So the packing factor is uh, equals to, the formula is pi by 6 diameter cube of cesium ion is the volume of cesium ion plus pi by 6 into diameter cube of chlorine. This is the volume of chlorine ion divided by A cube. This I will simplify as pi by 6 into diameter cube of cesium plus ion plus diameter cube of chlorine ion divided by A cube. I know the value of A. I have already calculated. So let us substitute the values. Pi by 6 in bracket diameter cube of cesium ion. The diameter of cesium ion is given here, which is 3.3. So in the bracket 3.3 cube plus diameter cube of chlorine ion. Diameter of chlorine ion is given 3.74. So this is 3.74 cube, bracket complete, divided by A cube. I know the value of A. We have just calculated value of A. This is the value of A. I am not converting. We are keeping all this in angstrom unit. So divided by 4.053 and cube of this. This is A cube. So let us simplify this further. Pi by 6 is equals to 0.5233 is the value of pi by 6. In bracket, cube of 3.3 is 35.937 plus cube of this 3.74 is equals to 52.31 divided by cube of this 4.053 is 66.5, and if you simplify this you get 0.695, that is packing factor. And so the packing efficiency is equals to packing factor into 100, that is equals to 69.5%. So we got the packing factor of the cesium chloride structure. Then last what we have to find is density, rho. Now you know the density is nothing but mass by volume. We are going to use that formula, mass by volume. In this case it is a mass of unit cell. Mass of atoms in unit cell divided by volume of unit cell. In this case, this is simple cubic diatomy. So effective atoms per unit cell, let me write that, effective atoms in unit cell equals to 1 cesium ion plus 1 chlorine ion. So the density is nothing but it is a mass of cesium ion plus mass of chlorine ion divided by A cube, which is the volume of the unit cell. Now mass of cesium ion, we know the atomic weight. Atomic weight of cesium is given over here 132.9. So it is 132.9. That is the mass of cesium ion in terms of AMU. Plus mass of chlorine ion. Mass of chlorine ion is also given, which is 35.45. So plus 35.45. This is in AMU. We have to convert that into kg. So to convert that into kg, we have to multiply it by 1.67 into 10 to the power minus 27. So we get the mass in kg divided by AQ. Now lattice constant for this is also we calculated earlier, which is 4.053. So this is a 4.053. This is in angstrom. We have to convert that in meter. So 4.053 into 10 to the power minus 10 meter and cube of this. If you simplify it further, what we get is 281.145 into 10 to the power minus 27 divided by 66.58 into 10 to power minus 30. Further simplification gives us 4.22 into 10 to the power 3, and the unit is kg per meter cube. So density is this. Okay, so this is the problem based on simple cubic diatomic. There could be the other problem also, like a rubidium chloride or cesium iodide, or maybe other some structures, some materials are having simple cubic diatomic structure. For all of them, you have to use the same method to find lattice constant, packing fraction, and the density. Then our fourth problem is based on FCC diatomic structure NaCl type. Okay, this is a FCC diatomic structure NaCl type, and that material is element is MnO, manganese oxide, has FCC diatomic structure. So, and here it is written where the oxygen ions are. Oxygen ions are at FCC positions, and manganese ions are occupying all octahedral whites. So when you get to know this, it means that this is FCC diatomic NaCl type structure, because in NaCl type structure, one ion occupy all the FCC positions and other ion occupy all the octahedral position. So this is a FCC diatomic NaCl type structure. And for FCC diatomic NaCl type structure, we know the formula to find lattice constant, packing fraction, and the density. So let's see what is given. The first is it is a FCC diatomic NaCl type structure. So when you say that it is FCC diatomic NaCl type, it means effective ions are effective atoms per unit cell. That is equals to 4 sodium plus 4 chlorine ions. So total 8 ions are there per unit cell, 4 sodium and 4 chlorine. And we know the formula. Let's see what is given here. Radius of manganese is given, Mn is given, and that is equals to 0.67. And so its diameter is equals to double of that, 1.34 angstrom. This is given. Similarly, the radius of oxygen is given, which is equals to 1.32 angstrom, and therefore the diameter of oxygen is equals to double of this, that is 2.64 angstrom. So this is given. Similarly, atomic weight of manganese is given, which is 54.938 AMU, and atomic weight of oxygen is equals to 16 AMU. So these are the given quantities. Now when it is FCC diatomic NaCl type, we know that lattice constant, in this case atoms are in contact, or these ions are in contact with each other along the edge. and that age is nothing but that is equals to diameter of sodium plus diameter of chlorine, because along the edge they are in contact with each other. This formula we already derived, you must remember that, and therefore A is equals to 1.34 angstrom is the diameter of, okay, manganese plus 2.64 angstrom is the diameter of oxygen. So this is the formula. A equals to diameter of sodium plus diameter of chlorine, or in general you can write A is equals to diameter of positive ion plus diameter of negative ion. So that is why A is diameter of this positive ion plus diameter of negative ion, and that is equals to, the sum is equals to 3.98 angstrom. So we got the lattice constant A is equals to 3.98 angstrom. Then we have to find the packing fraction. Now in the unit cell, there are 4 ions of manganese and 4 ions of oxygen. So instead of pi by 6, we will take 4 pi by 6. And in the bracket, diameter cube of positive ion plus diameter cube of negative ion, and that divided by diameter of positive ion plus diameter of negative ion cube. But this is nothing but A. A we already calculated. So you need not have to add and then take the cube of that. So therefore, this value of 4 pi by, let's write 4 pi by 6 in the bracket. Now diameter of positive ion is 1.34 cube of this, plus diameter of negative ion is 2.64 cube of this, bracket complete, divided by A cube, which is 3.98 angstrom. Of course, all are in angstrom, so that is cube of that. So let us simplify. The value of this 4 pi by 6 is equals to 2.093 in bracket. Cube of 1.34 is equals to 2.41 plus cube of 2.64 is equals to 18.4, and divided by cube of this 3.98 is equals to 63.045. So that is equals to 43.56 divided by 63.045, and that is equals to 0.69. So packing factor is equals to 0.69 and packing efficiency is equals to 69%. So we got the packing factor and efficiency. Then we have to find density. Now in this case, in the unit cell, there are 4 manganese ions and 4 oxygen ions. So we have to take mass of 4 manganese ions plus mass of 4 oxygen ions. That would be the mass of the unit cell. And that divided by volume of the unit cell, which is AQ. 4 here, 4 and here 4, so I will take 4 common. So 4 in the bracket. Mass of manganese is 54.938 plus Mass of oxygen is 16 plus 16, and that divided by, but this is in AMU. This 54.938 and 16 they are in AMU. You have to convert that in kg. So into 1.67 into 10 to power minus 27, then this value converts to kg. Divided by A cube, we know the A is this 3.98 angstrom. 3.98 angstrom. We have to convert this to meter. So into 10 to power minus 10 meter and cube of this. Then let's simplify this. So this is the 4 into 70.938 into 1.67 into 10 to power minus 27 divided by cube of this 3.98 is 63.045 into 10 to power minus 30, and that gives us the value of 7.5 into 10 raised to 3 kg per meter cube. So we got the density. So this is NaCl type structure. So we got the value of the lattice constant 3.98 angstrom. We got the packing factor and packing efficiency, and we also found the density. So this was NaCl type, diatomic NaCl type. Then we will take the example of FCC diatomic diamond type. FCC diatomic diamond type, and that example of that is here. Zinc blend. Zinc blend has diamond structure. So let us write what are the given quantities. Radius of zinc is given, which is equals to 0.83, 0.83 angstrom. And so diameter of zinc is equals to 1.66. Okay, it is 1.66. Similarly, radius of sulfur is given, which is equals to 1.74 angstrom, and so the diameter of sulfur is equals to 3.48. Of course, this is in angstrom. So this is given, and in addition to that, atomic weight is given, m. Atomic weight or molecular weight. Atomic weight of zinc is given, which is 65.37 AMU, and atomic weight of sulfur is also given, which is equals to 32.06 AMU, and it is a diamond structure. It's a diamond type structure. These are the given quantities. Now, when it is a kind of diamond structure, we know that basis ions or atoms are in contact with each other along quarter way along the body diagonal. So quarter of body diagonal is root 3a by 4. And along this distance, these two ions are in contact with each other. So this is equals to radius of zinc ion plus radius of sulfur ion. This is the easy way to remember. And hence A equals to 4 times radius of zinc ion plus radius of sulfur ion divided by root 3. So this is the formula to calculate the lattice constant. Let us substitute the values of this radius. So 4. Now radius of zinc is 0.83, 0.83 angstrom, plus radius of sulfur is 1.74 angstrom divided by root 3. And if you simplify this, what you get is 5.935 angstrom. Lattice constant E equals to 5.93 angstrom. So we got the lattice constant. Then we have to find packing fraction. To find the packing fraction, we know that there are 4 zinc and 4 sulfur. Total 8 are there. 8 atoms per unit cell in case of diamond type. So in this case, there are 4 zinc and 4 sulfur are there. And that's why packing factor, you should remember the formula for this. 4 common, so 4 pi into pi by 6 into diameter cube of zinc ion plus diameter cube of sulfur ion divided by A cube. Now A, you can substitute this formula for A, but since we already calculated the value of A, so I don't want to calculate it again. Okay, let's substitute the values. So this is 4 pi by 6 into bracket diameter cube of zinc. Diameter of zinc is 1.66. So 1.66 cube plus diameter cube of sulfur. This is the diameter of sulfur ion 3.48. 3.48 cube, and that divided by A cube. A is this, which is 5.935 cube. So let us simplify it. Value of this 4 pi by 6 is 2.093 into bracket cube of 1.66 is 4.574 plus cube of 3.48 is 42.144 divided by cube of 5.935 is equals to 209.05. So let us simplify further. Addition of this is 46.718, and that divided by 209.05, and that is equals to 0.47. So packing fraction is 0.47, and so the packing efficiency is equals to 47%. Then let us find density of this material, density. To find the density, there are 4 zinc and 4 sulfur ions in the unit cell, and hence density equals to mass of 4 zinc ion plus mass of 4 sulfur ions, and that divided by volume of unit cell, which is equals to A cube. Then we know the value of A. So here 4 is common. So mass of zinc, the zinc atomic mass is given 65.37 and sulfur is 32.05. So mass of zinc is 65.37 AMU plus mass of sulfur is 33.06 AMU. We have to convert that into kg. So 1.67 into 10 to power minus 27 kg. And this divided by A cube. We know the value of A. This is value of A, 5.935. So that divided by 5.935. This is in angstrom. So let's convert that in meter by multiplying 10 to power minus 10. So we get this in meter. Okay. Therefore, 4 into this addition is 98.43 into this 1.67 into 10 to power minus 27 divided by cube of this is 209.05 into 10 to power minus 30. And then after simplification you get 3.14 into 10 to power 3 kg per meter cube. So we solve all the problems like simple cubic diatomic, simple cubic monoatomic. Few problems we have solved: simple cubic diatomic, simple cubic diatomic, FCC diatomic NaCl type, and FCC diatomic diamond type. Let's take one more problem of NaCl here. This is the FCC diatomic NaCl type. In this case, calculate the distance between two adjacent atoms of the rock salt crystal. Packing fraction and its density is given. And its density. Given are atomic weight and the radius are given. So let us write what are the given. So radius of sodium ion is given, which is 0.98 angstrom, and therefore diameter of sodium is 1.96 angstrom. Similarly, radius of chlorine ion is given, which is equals to 1.87 angstrom, and so its diameter is 3.74 angstrom. This is given. In addition to that, atomic weight of sodium is given, which is equals to 22.99 AMU, and atomic weight of chlorine is given, which is equals to 35.45 AMU. So these are the given quantities. And what we have to find is the distance between two adjacent atoms. Now you know that along the edge, if this is the sodium, then this is chlorine over here, and this is the chlorine over here. So along the edge, they are in contact with each other. And this distance is interatomic distance, which is D. That we have to find. So to find D, first we have to find A. From here to here, we have to find A. So let's find from here to here is A. So let us find A. For NaCl type, we know that A is equals to diameter of positive plus diameter of negative ion. We know the diameter of sodium ion is 1.96 plus diameter of chlorine is 3.74 and that is equals to 5.7 angstrom. So this is the value of A. And what we have to find is D. So D is equals to A by 2. So 5.7 angstrom divided by 2. This we have to find. And that is equals to 2.85 angstrom. That is interatomic distance. Then we have to find packing factor. Packing factor formula is 4 pi by 6 diameter cube of positive ion plus diameter cube of negative ion and divided by A cube. I am writing only A cube because we know the value of A. Let us substitute the values. 4 pi by 6 diameter of positive ion, that is equals to 1.96 cube, plus diameter cube of negative ion, that is 3.74 cube, and divided by A cube, we know the value of A, 5.7 cube. So value of this 4 pi by 6 is equals to 2.093 in bracket cube of 1.96 is equals to 7.53 plus cube of 3.74 is equals to 52.31 and cube of this 5.7 is 185.193 and that is equals to 125.25 divided by 185.193 and that equals to 0.68. Packing factor 0.68 and so the packing efficiency 68%. Then we have to find the density. Now this is the NaCl types. So in the unit cell there are 4 sodium and 4 chlorine ions. So density is mass of 4 sodium ions plus mass of 4 chlorine ions and that divided by volume of unit cell, which is equals to A cube. So that's equals to 4. Mass of sodium is given 22.99 here and chlorine is 35.45. So 4 common, 22.99 plus 35.45. We have to convert this in kg, so into 1.67 into 10 to power minus 27 and divided by A cube. We know the value of A. This is A 5.7 angstrom. We have to convert that into meter. So 5.7 into 10 to power minus 10 meter and cube of this. So let us simplify this. What we get is 390.38 into 10 to power minus 27 divided by 185.193 into 10 to power minus 30 and that is equals to 2.11 into 10 to power 3 kg per meter cube. So far we solved the 6 problems. Let's go and find out. Let's solve the seventh problem, which is find out the local packing arrangement in the ionic crystal lead sulfate, PBS. Assume the crystal structure to be cubic. Calculate the density and lattice constant of the crystal. So let's see. It's a cubic crystal is given. We don't know whether it is simple cubic, body center cubic, or simple cubic diatomic. We don't know that. This is of course a diatomic, but we don't know whether it is a simple cubic diatomic or FCC diatomic NaCl type or diamond type. So cubic crystal is given. Then radius given. Radius of Pb2 plus is given, which is equals to 1.32 angstrom. And so the diameter of Pb is equals to 2.64 angstrom. Similarly, radius of sulfur is given, which is equals to 1.74 angstrom. And so the diameter of sulfur is equals to 3.48 angstrom. Atomic weight is given. Atomic weight of lead is given, which is 207.2 AMU, and atomic weight of sulfur is given, which is 32.066. So let us find what kind of unit cell it is. To find that what kind of unit cell it is, let us find critical radius ratio. Critical radius ratio is nothing but RC by RA. And RC is cation is 1.32 angstrom and anion is 1.74 angstrom, and that equals to 0.7583. Now we know that when the RC by RA is in between 0.732 to 1, this is ligancy 8. Okay, when it is in between. So obviously it is in between 0.732 to 1. So this is ligancy 8. So the structure is simple cubic diatomic. And when it is a simple cubic diatomic, we know the formula for lattice constant, which is diameter plus of diameter negative upon root 3. Diameter of positive ion plus diameter of negative ion divided by root 3. And this is already given to you. Diameter of positive ion is 2.64, this, plus diameter of negative ion 3.48 divided by root 3. That is equals to 6.12 divided by root 3, and that is equals to 3.533 angstrom. So we got the lattice constant. What do we have to find is lattice constant and density. So let us find density then. So density in this case, so this is a simple cubic diatomic. So there is a one lead ion plus one sulfur ion per unit cell. So mass of the unit cell is equals to mass of lead ion plus mass of sulfur ion, and this divided by volume of the unit cell, which is AQ. So mass of lead is given 207.2 and mass of sulfur is 32.066. So this is equals to 207.2 plus 32.006. This is in AMU. Convert that in kg by multiplying 1.67 into 10 to power minus 17. And that divided by AQ. A is this, but that is in angstrom 3.533. Convert that in meter and cube of this. So let us do the addition, which you get uh, let me do the calculations for this. So this is 239.206 into 1.67 into 10 to power minus 27 divided by cube of 3.53. Let me calculate it. So it is 3.533 cube, that is equals to 44.1 into 10 to power minus 30. Then this 239.206 into 1.67. So this is nothing but 399.474 divided by 44.1 into 10 raised to 3. So this divided by 44.1, and that is equals to 9.06 into 10 to power 3 kg per meter cube.